I'll start. Starting again, welcome everyone to synchrotron X-rays for micromechanical analysis. So this is lecture 2. So today, we're going to be talking about some basics of crystallography. We're going to be talking about orientations again, and specifically different ways of describing orientations. And then we're actually going to get into some X-rays. So we're going to finish off with Bragg's law. So if we're talking about crystallography, we have to talk about crystals. A crystal is a set of atoms that are periodically arranged. And by that, we mean it has translational symmetry. So that if you take a step that's equal to a very specific translational distance, your surroundings are exactly the same as where you were standing previously. And what's important is that the reason X-ray diffraction works is because of this periodicity of the crystal lattice, which we'll really dig into next class. And today, crystallography can be used for many things. It can be used for solving, for finding unknown crystal structures. But in this class, what we're going to be mostly interested in is looking at perturbations of known crystal structures due to load and deformation. So a crystal mathematically has two different parts. The two parts are the lattice And we also have the crystal basis. Which is sometimes called the motif. So a lattice, when we're talking about crystals, is just an imaginary set of constructed points in space. Hopefully we can see these. While the crystal basis is the repeating set of atoms which are tiled on each lattice point. So our lattice plus our crystal basis gives us our crystal. So this operation, this tiling operation where I've taken the crystal basis and I've tiled it onto the crystal lattice is called a convolution. And we'll talk about this a little bit more later on in the class. But the crystal is a convolution of the lattice and the crystal basis. And I just want to be a little bit careful here. I know I've called this the crystal basis, but we're going to be talking a lot about crystal lattice basis vectors. And so those crystal lattice basis vectors are associated with the lattice here. So I'm going to try to keep those straight. So now with our lattice here, if we want to talk about position in the crystal, we usually talk about lattice basis vectors. So we'll have a 2D crystal coordinate system here. And a crystal lattice basis vector is just a unit step in the lattice that you can move across and be in an identical position. And then using these basis vectors, we can describe a position anywhere, or we can describe any lattice point as a linear combination of the basis vectors. So a lattice point position X is just a linear combination of the lattice vectors. So now, what I did say previously is that the volume contained within the lattice basis vectors is called the unit cell. volume of the unit cell, B, can be found with this equation, which we'll be using later on today to talk about the reciprocal lattice. So, what's important to remember is that the crystal lattice can be completely defined by these three basis vectors. Draw one coming out of the page. And A3 is coming out of the page here. These three basis vectors completely describe the unit cell, but the unit cell can also be described by the 6 parameters that I'm going to list. So sometimes you're given these 6 parameters, which you can then figure out the unit cell from. So the first is usually referred to just as A, which is the magnitude of the first lattice basis vector. B, the magnitude of the second. C, the magnitude of the third. And then 3 sets of angles, alpha, which is the angle between A2 and A3. Beta is the angle between A1 and A3. And gamma is the angle between A1 and A2. So just a picture here. 1, 3. So this is C, this is B, this is A. This angle is alpha. This angle here. This gamma. And this angle here. Beta. So I drew an initial set of basis vectors here, but what's going to be really important, we talked a lot last class about how a coordinate transformation is just a set of angle cosines between a set of coordinate system basis vectors that are in 2 different frames. But if we're being careful here, these crystal lattice basis vectors are not the same as a set of coordinate basis vectors. And I think that confuses a lot of people. They're usually very closely related, and we try to pick a set of coordinate basis vectors that makes operations within the lattice basis vector easy. But that's not always the case for a complicated crystal. But what's usually chosen, might be easier to do over here, is that, and let's draw a complicated set of crystal basis vectors. So for a complicated set of crystal lattice basis vectors, when we're going to attach our crystal coordinate system, there's a usual convention just listed in a paper by Busing and Levy, 1967. And what we're going to do is we're going to make sure that our first basis vector, E hat C1, we're going to make sure that it's parallel to A1. We're going to make sure that E hat C2 is in the same plane as A1 and A2. And of course, E hat C3 has to be perpendicular to E hat C1 and E hat C2. What that means, if we choose this set of basis vectors, is that A hat 1 usually only has one non-zero component along E hat C1. A2 can have two non-zero components. While A3 can have three non-zero components. The last important bit to discuss about lattice basis vectors is that their choice is arbitrary. As long as we choose directions and magnitudes that bring us to a translationally symmetric position, that's a perfectly valid choice of basis vectors. So for example, simple crystal here. So one obvious choice of basis vectors looks like this. So this is usually picked, and then here our lattice points are here in the center. That's a fairly obvious one. That's a valid choice of lattice basis vectors. Another just as equally valid combination would have A1 going along the same direction, and we could have our second basis vector, star here, along this 45-degree direction into the center of an atom. So that's another perfectly valid set. And just as an example, a third set would be having the basis vectors point down, maybe like this. My last example would be, we could also maybe choose these smaller atoms as, or move the origin around to these smaller atoms. So I really just want to emphasize that the choice of basis vectors is arbitrary. So you have to make sure that if someone tells you what the basis vectors are, that you're clear that there could be another set that was just as easily chosen. With that being said, there are a few conventions that are usually followed, or a few sets of choices that are often taken. A few good choices. So people often choose a primitive unit cell. And that's a choice of basis vectors which contain smallest possible volume. On my little drawing over here, this is a primitive unit cell would actually be from one basis vector from these two atoms, and then this choice here to the second atom in the middle was actually a primitive unit cell. Because you can see that the volume enclosed by that unit cell is smaller, or the smallest possible, but we can see that it's smaller than one contained by my first choice. Another good choice which is often made is to place the origin at the center of an atom. Or the center of an atomic position. And the last choice that's often made is that orthogonal basis vectors are often chosen for materials with cubic symmetry. The next thing I want to talk about are lattice planes. So we care about lattice planes in this class because all our understanding from how the crystal is behaving our understanding of crystal response will come from measuring changes in lattice planes. Using X-ray diffraction. So these are what we're actually going to be tracking. And so what do I mean by a lattice plane? So lattice planes is, or a set of lattice planes they are parallel planes that are periodically stacked to the crystal. So just like our lattice points, the lattice planes are another construct. These aren't something that you can go look at, a set of lattice planes. These are just planes that we draw through a crystal. It's a note. These planes do not have to pass through atoms.
But the basis vectors have to pass through atoms. When you choose,
they don't.
They don't.
They don't. So that choice can be arbitrary. You can put the origin anywhere, but that's, like I said, it's more convenient to maybe say put the origin of the basis vectors at an atom. But you also could have moved it. As long as you can make a translational step across the unit vector and be at a symmetrically equivalent place, that's okay.
Okay.
And if you couldn't hear that online, that question was, do lattice basis vectors have to pass through atoms? And they do not. So these sets of planes are defined by their plane normal, n, and their spacing, e. And we can have, there's more than one set of lattice planes through a crystal, and they can be oriented in different ways with respect to the unit cell. And the way that we denote different sets of lattice planes is by their Miller indices. And these indices are denoted by the integers h, k, and l. And I'll use a script L just so it's easier to see. These integer values tell us about the orientation of the set of lattice planes that we're looking at with respect to our crystal lattice and the crystal lattice basis vectors that we've chosen. So for example here, we have a set of lattice planes with h equal to 2, k equals to 3, l equal to 1. The lattice planes will intercept the basis vectors at the fractional inverse of the Miller indices. So with h equals 2, the planes will intercept halfway across A1. For k, it'll be a third of the way across A3. And L will intercept at the top, or A2, and then L will intercept at the top of A3. And the plane, something like this. So these Miller indices are kind of nice for visually seeing what the planes are like, but as I'm going to show in a sec, they're actually kind of hard to work with if you only have the direct lattice and the Miller indices. Because what you really want to know is something like, what is the plane normal for the, say, something like these lattice planes, so like these 2, 3, 1 lattice planes. So I've got a quick example here. Which will show how you calculate something like a plane normal. And this is hopefully going to motivate how useful something like the reciprocal lattice is, which we're going to use in a sec. We're going to find the normal direction. N of a set of 2, 1, 1 lattice planes in a cubic crystal. We have our cubic crystal and the 2, 1, 1 lattice planes. Intersect halfway across A1, at the end of A2, and at the end of A3. So here's our plane. But this doesn't tell us anything about the normal direction. But what we do know is we need to figure out what the normal direction is. We need to find 2 vectors which are in the plane, and then take the cross product of those to find the normal direction. And so our first vector is going to be from halfway across A1 to A2. Come back. It's going to be, it's going to be from A3 to halfway across A1. And from A3 to A2. That's going to be here. And what we actually find, if we work through all the math here, V1, so we want to find the normal direction, so that's V1 cross V2. That's equal to A3 cross A3 minus A3 cross A2 minus 1/2 A1 cross A3 plus one-half A1 cross A2, which is pretty brutal. It'll take quite a bit of time to work this out. What we find is that it's equal to A1 plus 1/2 A2 plus 1/2 A3. What you'll find is if you express that, we multiply that vector by 2, we get 2A1 plus 1A2 plus 1A3, which looks a lot like 211. So that's actually a nice thing about cubic crystals, is that the directions that lattice plane normals are pointed, you're given HKL indices, those are actually equal to just integer multiples of the basis vectors. That does not hold for any other crystal type. So I think people get confused pretty easily that as soon as you get to something more complicated, they've seen things like, well, the 211 normal is along the 211 direction in real space or in the direct lattice. And then they want to do that for more complicated crystal types. That does not hold. And this gets even more complicated as the crystal basis vectors are non-orthogonal anymore. The last bit of crystallography we're going to talk about today is the reciprocal lattice. So the reciprocal lattice is a construct, it's our third one today, between lattice points and lattice planes. This reciprocal lattice is another thing that is a construct. It can be kind of pretty intimidating for people starting to deal with this kind of thing if you're don't have like a solid state physics background. But for our purposes today, all we're going to use is something that makes the fraction calculations easy. So let's not worry about interpreting it too much, but we're just going to use the reciprocal lattice like a tool, which is going to help us figure out when diffraction occurs. Because we'll find that calculating diffraction events is much easier using the reciprocal lattice rather than the real lattice. Again, another construct. Formally, it's the Fourier transform of the direct lattice, or the we're not going to worry about this part too much. I do want to talk about how we calculate the reciprocal lattice basis vectors. So the reciprocal lattice basis vectors can be calculated directly from our real space or direct basis vectors. So V1 is equal to 2 pi over V. So remember, this is the volume of the unit cell. We brought up earlier. The ordering of these cross products matter here. So this is A2 cross A3, A3 cross A1, and A1 cross A2. So I see that. I'll try to start drawing the subscripts larger. Sorry, I missed that previously. Catch that. Two, three. I'll try to draw the subscripts larger. And so the ordering, and like I was saying, the ordering of these cross products matter. The reciprocal lattice vectors are constructed.
There's one more question.
Yes.
It says fix the focus of the camera.
Pass me the remote right there, the left.
This one.
Yep. So I'll try to only use a smaller bit of the screen. The reciprocal lattice vectors are constructed so that the dot product between a real basis vector and a reciprocal lattice vector is equal to two pi if it's, say, A1 dot B1 and it's 0 otherwise. A reciprocal lattice vector, G, is equal to H times B1 plus K times B2 plus L times B3. And I've chosen, or I haven't chosen, but H, K, and L have been chosen for these integers because a reciprocal lattice vector is intimately tied to the lattice planes in real space. The spacing D of a set of lattice planes with the Miller indices H, K, and L is equal to 2 pi over the magnitude of the reciprocal lattice vector, which has the same indices, and plane normals are pointed in the same direction as the reciprocal lattice vector with the same Miller indices. And so I'm using these double bars as a magnitude descriptor here. And so what I wanted to show previously when I calculated out that lattice plane vector was that it's a difficult process, or the lattice plane normal is a difficult process. What instead is a better option is once you write a code one time that can calculate reciprocal lattice vectors, you can directly calculate plane spacings and normal directions without having to think about it. So that's one of the useful, along with the fact that it's easier to calculate diffraction, it's also just a lot easier to figure out crystal geometry using the reciprocal lattice. So that's it for crystallography. We're going to talk about orientations, and specifically for just a little bit longer, and then that'll be it for building up our tool set that we're going to use. And again, an orientation. For the rest of the class, I'm going to use an orientation and a coordinate transformation kind of interchangeably. So when I'm talking about a crystal orientation, I'm talking about a coordinate transformation from a crystal frame to an external frame. Note, and in this class, that's either going to be related to the sample or the lab. Notationally, I'm going to try to keep track of which frames that the coordinate transformation transforms between in superscripts. So just for example, I might have, I'll usually be using A for a coordinate transformation, and I'm going to have here an S, comma, C. And what this is going to transforms from crystal to sample. So I have it set this way, so that the frame that we're transforming to is going to be on the left, and the frame that we're transforming from is on the right. Because then I can write things like this, or a vector expressed in the crystal frame, and its components here in the sample. So the side that it operates on are matched up and they're closer. So that's just the notation that we're going to follow here. So coordinate transformations have a lot of properties, and some of them are going to be pretty useful for us in the future. One thing that's important to note is that coordinate transformations are not commutative. So ordering matters. Second, then orientation times its transpose is equal to identity, which is a useful property, but it also says some important things about the nature of a coordinate transformation itself and how much information is contained in it. So if we write this out in indicial notation, what we have here is 6 independent equations. So if we have a coordinate transformation, as we read out, there were 9 cosine angles to begin with that are related by 6 equations. There's only 3 independent pieces of information. So with only 3 independent pieces of information, we generally don't have to record or save a full coordinate transformation in order to record all the information necessary to save it for a lot of our codes. And there's several different ways of kind of coding or parameterizing these 3 different pieces of information, which I want to talk about. So the first, so we've talked previously a lot about rotation, or these matrices here, these 9 cosine angles, which are referred to as rotation matrices. Which I think contributes to a lot of confusion between rotations. and coordinate transformations, but we'll stick with it. If we're listing the full 9 numbers in a matrix, we'll call it a rotation matrix. Another way of describing a coordinate transformation are Euler angles. Five. So any coordinate transformation can be broken into 3 transforms let's insert here 3 sequential around perpendicular axes. A coordinate transformation around E1. So E1s from the sample happened to be equal to the crystal transform. And just for shorthand, C is going to equal to cos omega, and S will equal to sine omega.
But only in the matrix you're about to draw.
Yeah,
Over
that's
there, it's
sample
and crystal, right?
crystal. Yeah.
I'm just going to shorten it to cos and sine.
Okay.
Keep that clear. One, go. Note, so this is how I've written these, this is clockwise positive. If they share the second coordinate axis, and then sharing the third axis. So I took the time to explicitly write this out, mostly because of this sine term right here. This one can kind of get you in big trouble. There's a natural tendency that you see these blocks, cosine, minus sine, cos, and they want to maintain that block. I've lost weeks of time of my life to this minus sign right here, to something being backwards in a diffraction code. So be very, very careful. So, and what we can do is we can make a coordinate transformation out of any combination of these three transformation matrices, and we can keep track of the three angles. What we have to make sure is that we do have to alternate them. So you can't make a coordinate transformation from 1, 1, and 1. You can do it from 1, 2, and 1, but they do have to at least, or you can't do 2 sequential rotations around the same axis in a row. So they do have to alternate in that form. You could do 1, 2, 3, but you couldn't do something like 1, 1, 2. You cannot make a general rotation. So something like 1, 1, 2 is bad. 1, 2, 1 is okay. 1, 2, 3 also okay. And an often used form in crystallography for Euler angles is the Bunge convention. Bunge was one of the pioneers of texture analysis, the study of distributions of crystal orientations. So if you delve deeper in this topic, you'll see Bunge come up a lot. And Bunge's ordering was 3, 1, 3. So generally, if someone gives you a set of Euler angles describing a crystal orientation, it usually follows the Bunge convention. Another often used one is the Cox convention. So that's one way of describing orientation. You can just give someone 3 Euler angles. Another way that we're going to use in this class are angle axis parameterizations. And so any coordinate transformation can be described by a set of normalized like I said, normalized vector components. Which remain unchanged under transformation. So what does that mean? So sometimes this is referred to as the rotation axis of the rotation. This set of words that I've written down here. But I think that's a little misleading with the coordinate transformation because we're not actually rotating anything. But essentially, for any coordinate transformation, A, there always is a set of components T which remain unchanged. And this can have any magnitude, but there is, we'll leave this as a normalized vector here. But we can use this as part of the information that we can use to describe a coordinate transformation. And then for shorthand, this will be the axis part of our angle axis parameterization. And then there is the angle omega. So we can use this as the axis that we transform about, and this is the angle omega. So we've got our angle omega and our axis T. If we want to record these, there's a whole family of vectors we can build using these two values. Which have the form this Ri is just a vector So we can have a function of omega times our axis. And the simplest is just that the magnitude of the vector is equal to the rotation angle here. So this is just called angle axis form. And another often used one is called the Rodriguez vector, where this function here is the tangent of the rotation angle divided by 2. So Rodriguez vectors have very nice properties for plotting and moving through distributions of orientation. And we'll get into that a little bit later. Or I've got a set of notes which I'm going to post online or I'll send out to the class. The last bit I want to get to today is Bragg's law. We got to do a little bit of diffraction. Be too much to do 2 full classes and never talk about it at all. So Bragg's law is kind of nice. It's descriptive. It kind of shows a nice picture for getting us started for diffraction, but you'll find out pretty quickly that it's not particularly useful for calculating when diffraction occurs from a randomly oriented crystal. You'll find that if someone just hands you a crystal, says this is the orientation, can you tell me how to spin it in order to make diffraction occur? Bragg's law is not going to help you too much. So that's why I just want to talk about it quickly today, and then we're really going to dig in the next class. But I think the best way for starting Bragg's law is so how should lattice planes the order in a crystal be oriented so that diffraction, that's not diffraction, so that reflected X-ray amplitudes add constructively. So the only way I personally know how to set up this problem is setting it up almost while knowing the answer. And the next time we're going to build things from the ground up where we don't necessarily know what the answer is. But what we do know is that for amplitudes of electromagnetic waves like X-rays, so hopefully that's about as physicsy as I get in this class. Only time I hopefully don't have to bring up electromagnetic waves too much. But for constructive interference path lengths that X-rays travel must be integer multiples of the wavelength. I'll use lambda. So m lambda must be equal to the difference in path length. So let's look at our crystal. We've got a set of lattice planes here. The normal n, the spacing d. And we're assuming that we can orient this crystal in such a way that incoming X-rays can hit a set of lattice planes and reflect at an angle theta. So just notice, you see I've made a lot of assumptions already. We're assuming that there's some way that we can orient this crystal and so that we can get constructive interference, with this idea that X-rays reflect, with reflect being maybe not the best word to use, but it's often kind of used colloquially, but we can say that the X-rays are reflecting off a set of lattice planes. And so if these X-rays are reflecting off a set of lattice planes and we're a far distance away, the only difference in path length travel from the source over here sorry about this. Crystals to form before we started loading it. Yes, theta, theta. If we look at the geometry, our path length difference between these traveling X-rays is this little segment here, and this little segment here. So this little segment, we do the geometry. We have like triangles. This is theta. So this segment here, delta p, so this is half our path length distance. It's equal to d sine theta. And the total path length is equal to 2d sine theta. So going back, it's now putting everything back together again. This idea that for constructive interference, the path length has to be equal to a wavelength or an integer multiple of the wavelength of the incoming X-rays, we find that m lambda equals 2d sine theta. And this is our famous Bragg's law. So we're here. So this is one way of describing the diffraction condition. Unfortunately, there's kind of some problems here where, one, we had to know which way this plate normal was facing, and we had to get it in the plane to the incoming and reflecting beams. And we'd have to be able to rock the crystal about an axis coming out of the page in order to get this theta angle correctly. So it's not particularly useful when someone just gives you a crystal and goes, here's what's the orientation of this, because you have to know that ahead of time. So we're going to dig in next week, and we're going to talk about a more comprehensive vector-based approach for figuring out the diffraction condition. The one other thing I wanted to talk about is we typically, if you see here, the difference between the incoming and outgoing beams. This angle is 2 theta. And the last bit is something that will come back later, is this integer multiple. So if we know we have a monochromatic X-ray beam, so only one wavelength coming in, we don't have to worry about this integer multiple too much. But it is very important if we have a polychromatic beam hitting the X-ray. So what actually happens is if we have a fixed crystal and a polychromatic X-ray beam, multiple wavelengths are diffracted at once. So that's something that's going to come up a little bit later. But for a lot of experiments that we do, we don't really have to worry about this integer too much, so we can get rid of it. And so that's it for today. Next week. We're going to be talking about the scattering vector. The Lowry diffraction condition. And rotating crystal diffraction experiments. So we're going to want, after next week, we're going to be able to calculate the angles at which diffracted X-rays occur. And this operation here is at the heart of most modern X-ray diffraction codes that we use here at Chess at the synchrotron. So thank you, and see you next week.